In this video, I am going to start discussing how to interpret mass spectra. And of all three of the techniques used in organic chemistry, which is IR, mass spec, and NMR, obviously there are others, but those are kind of three staples. I think mass spec is probably the most difficult to interpret. IR, once you see a few of them, they are pretty easy to interpret. Seeing things like the alcohol stretch or the carboxylic acid stretch and things like that, those can become fairly easy to interpret. NMR, which is what I'll talk about in future videos after this one, are a little bit more difficult to interpret than that, but I think mass spectrometry is probably the more difficult one to interpret, at least for me it is, because there are a lot more sort of exceptions to various rules, and because we are putting it into this pretty extreme environment with all these electrons and these fragments coming off, we end up getting a lot of really weird things happening quite often, and so that can start adding some layers of complexity onto it. But anyway, that is kind of my opinion on mass spectrometry, but now we can talk about how to actually start trying to think about interpreting these things. So remember, in the previous video, we discussed how molecules in a sample are split into fragments, and those fragments will have a mass that is less than or equal to the mass of the entire molecule, which is called the molecular ion. And the fragments will have a charge that is almost always going to be z equals plus 1. So we don't usually get charges that are greater than plus 1 on these. So we therefore say that we are detecting fragments with a mass to charge ratio of m over z, and the relative amount of each fragment that will be detected is based on the stability of those fragments. And that stability is going to be based on things that we already know from the stability of molecules. So, for instance, a carbon that has more substituents on it is going to be more stable as a positively charged carbocation. So like a methyl carbon is going to be less stable than a primary, which is less stable than a secondary, which is less stable than a tertiary. And so what we'll see is that fragments that have carbons that are, say, tertiary carbocations are going to be more abundant than ones that are secondary, which are more abundant than primary, and those are more abundant than the methyl carbocations. And also molecules with resonance structures are more stable. So we'll see that things like the allylic carbon are going to be where splits occur more often than on non-resonance stabilized structures. In the previous video, we saw this scheme right here for the fragmentation. So we have our molecule right here. We are hitting it with these electrons so that it ejects an electron from the molecule. So we have the electron that we shot at it and the one that ejected. So two electrons come off. And then we have this right here, which we can call our molecular ion. And so this is a radical carbocation usually. And so we can think of it like this. So we have our electron, say we're hitting methane with it. We're going to eject one of these electrons right here. So we have our electron, we shot at it, the one that's ejected, and so we end up with something like this. So we have a bond made from an unpaired electron, and then that also makes it positively charged. So that is our M plus radical cation. And so what's going to happen after that is then we can start breaking pieces off of this. So we could have this hydrogen leave right here as just a radical, but we could also break this apart right here. So usually we draw it like this. So we draw it like that and put a bar pointing towards the direction where the positive charge will be. And so we'll end up with something like this. So now this thing that had a m over z of 30 is going to be split, and now we have an m over z of 15 right here, which is our methyl carbocation. But we'll also see this right here. And in fact, this will probably be even more abundant because we see this is now a primary carbocation rather than a methyl carbocation. And so those are the types of fragmentation that we will get. So these uncharged radicals do not actually show up because only the fragments with a charge will actually be deflected or accelerated in the magnetic field, which is why we use the m over z here. So like this one right here would not actually show up, neither would this one right here, because those are uncharged radicals, and so those will not be bent or accelerated or even detected by our mass spectrometer. So different fragments appear in different quantities, as I said, based on their stability. The height of the peaks in the spectrum reflect the quantity of that fragment. And so all the peaks are actually normalized to the highest peak, which we call the base peak, which is set to 100%. And the peak with the greatest mass will show up furthest on the right, which is the molecular cation. And so if we think about it this way, so we have this is what our mass spectrum will look like. So on the y-axis we have the abundance, and on the x-axis we have our m over z. And so our molecular cation will show up maybe somewhere over here, so we'll get a peak right there. They are usually not the base peak, so those are usually not the tallest ones. And so we can put, say, 100% right there. And so our base peak, which will show up somewhere to the left of our M plus peak right there, will show up somewhere over here, and that will go all the way up to 100%. And so this is our base peak here, which will be some fragment of our molecular ion. Like I said, usually the molecular ion is not the base peak, and so the base peak will show up somewhere to the left of the molecular ion. And what we'll see also is that we can have peaks that are actually heavier than the molecular ion, and that will come from the isotopes that we have. And so we might have one like this that we call the M plus 1. We might have another one here, and we call that the M plus 2. And so we can get peaks that look like that I will discuss here in a little bit. But anyway, those are two important peaks that we'll see. There will also be other peaks on here, so usually they will be some distance away from each other that can be predicted by the size of the fragments, and they will have a height that can be predicted by the size of the fragment. So we might have something right here that is 33%, and then we have this one over here, which is maybe like 10%. And so that's telling us that this peak right here is from a fragment that is less stable than this fragment, but this fragment here is from one that is less stable than the base peak, where the base peak will usually be the most stable of our peaks, or the most stable fragment that we get. And so, as I said, the abundance is calculated like this. So we have the number of detections for some fragment divided by the number of detections for the most abundant fragment, and then we multiply that by 100 to get the percentage. And so for the base peak, what we do is just divide the number of detections for the most abundant by the number of detections for the most abundant. That will come out equal to 1. Multiply that by 100, and so that's why that is given the 100% for it. If we just have a linear chain like this hexane here, we can get these fragments here. So we can get one that is 29, so that is this plus this here. So carbon is 12, so that's 12, 24, then 25, 26, 27, 28, 29. And so that fragment will have an M over Z of 29. But if we add one more CH2 on it, that's 43. Another one will bring us to 57, another one to 71. And then if we just broke this one off right here, that would be 15. So it's 12 from this plus 3 more, so that would be 15 right there. But we see that if we have, say, some substituent on it like this, now instead of just getting these primary carbocations, we can actually get a secondary carbocation. So we could break it either this way or this way. In one way we get M over Z of 71, where we have a secondary carbocation. The other one we get M over Z of 43, where we have a secondary carbocation. And so our mass spectrum will actually look like this. And so we see our base peak is actually this M over Z equals 43, and then we have this other relatively high peak, which is M over Z of 71, and the 71 is less likely, and that's because when we are splitting this off, we have to have this come off, and that will be a radical, remember. And so that would actually be a methyl radical, whereas if we are splitting off right here, we have a primary radical, which is going to be a more stable radical. And so that's why the 43 here is going to be more abundant than the 71, because when we split off the 43, we are making a primary radical rather than a methyl radical. And so that's why the M over Z of 43 will show up more. And so we also see here, like I said, the molecular ion is usually not going to be the base peak. And actually what we'll see in the future here is, sadly, quite often the molecular ion doesn't even show up. And so that's really not uncommon for the molecular ion not to show up, which is kind of a shame because that would be nice information to actually have. But anyway, this is looking at if we have a substituent on it that allows us to have a secondary carbocation. But if we can have a tertiary carbocation, that's even better. So if we have two substituents on this same carbon here, we can then have this split off where we have a methyl split off, or we can have this right here. So this isobutane right here split off. And so then we can get an M over Z of 85 or an M over Z of 57 right here. And so if we look at the spectrum for this, what we see, so the molecular ion actually doesn't show up. As I said, that's actually going to be quite common. We have our M over Z of 57 as our base peak. So that's this one. And again, that's going to show up more. In fact, it looks like the M over Z of 85 is not even showing up on here. And so that's because we would have to be making a radical methyl carbon right here, where instead of a radical primary carbon. And so we get the M over Z of 57 as our base peak, and that's going to be the most abundant one. And so we can also see here we have our M over Z of 43, which is if we broke it off at the secondary carbon here, so that we generated a secondary carbocation. And so although we see that the peak is higher than most other peaks on here, it's a lot smaller than our M over Z of 57 because the tertiary carbocation is going to be more stable than even the secondary carbocation. And so that is looking at the substituents on carbons giving us stability. The other thing, as I said, is the resonance stabilization. If we look at this trans-2-hexene here, we have an allylic position. It's going to break at this point a lot more often. That's because we have this resonance stabilization here at M over Z of 55. And so we see in the spectrum for it that the M over Z of 55 is our base peak. And so that is what we would expect because that's going to be the most stable fragment that we get from it. And this one, luckily, we do have a molecular ion actually showing up here. And so, like I said, that's often not going to be the case, but it's really nice if it is the case. And so another resonance stabilization that shows up quite often when we have these benzene rings. So say we have this benzyl group here. So that means we have this carbon right here bound to our benzene group or our phenyl group right here. We break off this R right here. So we end up with this resonance stabilization going on right here. But what you often see also is that we get this tripolinium ion. And so this will give the same fragment size as if we didn't consider the tripolinium ion. But what's happening is we are just seeing an alkyl shift. So this bond right here is just shifting up onto that carbon right there. So we end up with this 7-member ring rather than a 6-member ring with this sort of primary carbon sticking up off of it. This is a fragment that you see quite often as well. We can compare the benzene ring to the hexane ring. So this is not the benzyl ring anymore, so we don't have this carbon right here. So if we just break something off of a benzene ring, we get an M over Z of 77. If we do it off of a cyclohexane, we get an M over Z of 83. And so those are fairly common fragments to see as well. So this is just a list of the common alkyl fragments that we will see. So our methyl, which will have a peak at 15, ethyl at 29, 43, 57, 71, 85. So those are all very common ones to see when we have these linear backbones. Then our benzyl, which can turn into that triplennium, which was the 91. Then just the benzene is 77, cyclohexane 83, and cyclopentane 69. So these are common alkyl fragments that you will see in your mass spectra. And as I said, because of the sort of harsh conditions of the electron spray, for instance, you'll often see one sort of hovering around these values as well. And that's just because you can tear off some of these other hydrogens here and make these radical cations with it. And so you'll see fragments around, say, 28 or around 14 and things like that. So we can even look up here. So we have these other small fragments around here. We have these other small fragments around here. So we have a fragment here at 43, which is one of our common fragments, but then you see those other fragments around, which you see quite often because of the harsh conditions tearing off other hydrogens along with it. So it's very common to see those other peaks there in your mass spectra. And so the other thing we can think of are the heavier isotopes. So our molecular ion is the one with the same mass as the molecule. But if we have atoms in it with isotopes that are quite common, as we will see, we can get what are called the M+1 or M+2 peaks and so on. So these characteristic M+1 and M+2 peaks can be used for discerning if a particular element is present. And so we want to look at the abundances here. And so ones that are used quite often are these, because these isotopes right here are quite abundant, and so their M+2 peaks can be seen fairly easily, as well as these sulfur peaks right here are used quite often for determining whether sulfur is present. And so when we have the bromine, we will have an M+2 peak that is the same size as our molecular ion. So that's because the bromine 79 is about 50% and the bromine 81 is also around 50%. So those two peaks will be roughly the same size, where with the chlorine we have an M+2 that is a third the size as the M+ peak. That's because we have 75% of the chlorine 35 and around 25% of the chlorine 37. And then the iodine isn't an isotope here, but what we will see if there is an iodine present is a very large gap, so a 127 AMU gap in our spectra. So then with nitrogen, what we see is that we get an odd M+ peak with even fragments. So as we saw up here, all these fragments right here are odd numbers. And so that happens when we just have like an alkane, essentially. When we have a nitrogen in it, what we see is that our M+ peak will be odd, but then our fragments will actually be even. So instead of getting these odd fragments right here, we would actually get even fragments when we have nitrogen involved. Then for sulfur, we see an M+2 peak that is slightly larger than usual, about 4% of our M+ peak. And so if we look at some examples of these, so first we'll look at the chlorine. So this is just this ethyl chlorine right here. And so we see we have an M+ peak, and then this M+2 peak right here, which is about 1/3 the size of that M+ peak. And so we can see over here, this is the ethyl group that is coming off of here when the chlorine is broken off of it. And so we see these peaks around M over Z of 29 and 28. So remember the 29 here is our ethyl group. And so we see that after the chlorine has broken off. But our molecular ion peak, where we still have the chlorine attached, will have these two different peaks here because we are breaking off just a single electron. And so this will have the chlorines of the two different isotopes for it. And so then if we look at this with bromine, so we have ethyl bromine here. Again, we have our MOR-Z of 29 right here. And so right here we have our molecular ion and then our M+2 right here. And those are right about the same size. And so seeing two peaks like that is going to tell you that there is probably a bromine in your molecule. And then we have here with the sulfur, so we just break off this sulfur right here so that we end up with this propane cation right here. And so we have our molecular ion, and then we have an M+2 right here that is about 4% the size of that molecular ion. And so then right here, we're looking at our iodine. So we have an M/Z, so this is our molecular ion of 184, and then this is our peak here after the iodine has come off, and that is exactly 127 AMU lower than the molecular ion, and that tells us that this contains an iodine. And we can also see a peak right here where we actually have the iodine cation. And so that is going to be right at 127 right here. And so, like I said, we have amines and alcohols, which are going to give us some different types of peaks where the amines have the even numbered fragments. So compounds not containing nitrogen will usually show an even numbered molecular ion and mostly odd numbered fragments. And so some compounds, like alcohols, may fail to give a visible molecular ion. And as we've already encountered, this is also true for things that don't have alcohols. It's not uncommon for you to not see your molecular ion. And so if the molecular weight is odd with some major even-numbered fragments, then that is a good indication that there is a nitrogen in that molecule. And so if we have this 2-amino propane here, what we see is we have an M plus right here that is odd, and then all of our major peaks here, so like our base ion peak, are going to be even, and that tells us that we probably have a nitrogen present in this. And so with alcohols, what you see is you get even more complex peaks quite often. And this is one of those things where, like I was saying at the beginning of this video, the mass spectrum can often be one of the more difficult ones to interpret. And that's because if you do have these alcohols, then you can get these multiple different types of fragments here. So we can get this MOR-Z of 59 if we break it off right here. We can get this MOR-Z of 56 if we instead break it off right there. And we can get this MOR-Z of 45 if we instead break it off right there. And so we have multiple types of fragments we can get just because of the fact that we have this alcohol present. And so if we have the alcohol over here on the primary carbon, we can then get this resonance stabilization if we actually break off this right here. So if we break off this methyl group right here, we then get the carbocation on this carbon right here, and then the alcohol can actually come off as well, and that will come off as a water right here, and that allows us to get this resonance stabilization. And so we will get this MOR-Z of 55. And so we see that we have multiple things coming off of here now. So we have this methyl group coming off, but then we are also losing this alcohol as a water. And so that is giving us this peak that we will see at MOR-Z of 55. And we can also get this right here. So if the methyl group doesn't come off, but we just lose the alcohol group as a water, then we will see an M/Z of 70. And so quite often you will see fragments that look like this if you have an alcohol present on it. And so again, looking at this odd and even thing, we have the M/Z. So if we have the molecular ion, which is going to be a radical cation right here that is even, but then when we break something off, we get odd numbered fragments here. And we can also see that here when we have this allylic carbon, when we fragment off on this allylic carbon, that this M over Z is going to be odd here. So our fragments are usually odd. But if we have an alcohol, we see that we can end up with a lot of even fragments. So we can get these even fragments like this, but we can also get odd fragments like this. And so again, this is one of those things that can be confusing when trying to interpret mass spectra, and one of the reasons why I think the mass spectra can be the most difficult of sort of the triad of organic chemistry measurement instruments. This is just one of those things that you have to try and watch out for. And it's one of the reasons why it can be nice to get a molecular ion, but again, as I said, it's not uncommon to not get the molecular ion. And so when we have a nitrogen in it, again, we will see an odd molecular ion here, but then our fragments are often even. So we can get these iminium ions right here. And so that will give us these even fragments. Here we have an ether, and so this is going to be even, but then when we fragment this, so we're breaking off right here, we end up getting these odd fragments here. Or we can break it off this direction here so that the cation goes onto this R group, and now we are getting odd fragments again. And so we can also break it off over here. So we're breaking it off right here. That R group is coming off right there. And so that's an alpha cleavage, and we will again get odd fragments from these ethers here. And so we can have this M over Z even, so we are now looking at this ketone here, and so we are breaking it off right here, so right at that carbon. And so we can get this acylium ion right here, which is going to be odd. But there is also another type of fragmentation that we can get when we have a carbonyl on here. And so this is what's called the McLafferty rearrangement, and this splits out alkenes. So this alkene here and this alkene right here. And so we are breaking it off here at the alpha carbon. So we're breaking it off right there, and these will become the alkene right there. And so the mechanism for this looks like this. And I've seen other mechanisms for this, but this is maybe just a good way to think about it, probably the easiest way to think about it. So we have our radical cation right here, and so there is a radical at some point. Like I said, I've seen multiple types of mechanisms. One of the places I've seen the radical put is right here on the oxygen, and so we get something that looks more like that, but we're just going to look at this sort of schematically right here. So we can have the electrons from this carbon-hydrogen bond going over to the oxygen, these ones going down here to form a double bond right there, and then this bond right here is breaking. This is our alpha carbon right here. This is our beta right there, and this is our gamma. And so we're breaking between the alpha and beta and forming a double bond between the beta and the gamma. And so we are breaking off this piece right here. Then the fragment that we can usually detect is the one that still has the oxygen on it right here. So that will be a radical cation there. And so this is, as I said, the McLafferty rearrangement. And there are also different types of McLafferty rearrangements where it breaks it off at different points. And you can get McLafferty rearrangements in esters. And so again, this is just adding more of that complexity to these mass spectra that can make them difficult to interpret. One resource that I found online that's pretty good, and I will link to this in the description down below, is this right here. So I found this online, and this gives some fragmentations for things like ethers and esters and stuff like that. So it gives some very common fragments. So you can go through this. So we can look at our ethers. So we can get alpha cleavage. We can get this inductive cleavage. We can get this rearrangement. And so it gives some fragments for these. And then we can look at aryl ethers here, and so it gives some possible fragments for that. It gives amines, and so it goes through multiple different types of amines, including the cyclic amines. Then we can look at carbonyl compounds and aldehydes, aromatics, aliphatic ketones. So, like I said, this thing here is many pages long, and so that adds to that complexity of our mass spectra. So it adds to the complexity of our fragmentation on the mass spectra. So, like I said, this can all start getting really complex when you start really digging down into it. So if you're taking just like a sophomore level organic chemistry class, a lot of times they're really just going to ask you about some of these more common fragments. So they're going to want you to find these types of fragments right here. They're going to want you to be able to identify things like the bromine and chlorine, so the M plus 2s on those, that the iodine is going to have that 127 gap. They're probably going to want you to at least know the basic McLafferty rearrangement and what types of fragments you can get from that. Probably also that the amines are going to have these even numbered fragments on it. So if you see these even numbered major fragments here, then that is going to tell you that there's probably an amine. And so it's at that level of understanding and being able to interpret these spectra that you would probably be expected to know at a sophomore level organic chemistry class. But like I said, this can all start getting quite complex as you try to interpret it even more. But if you compare at least this basic level of being able to interpret these spectra with your IR and NMR data, then you can probably guess the molecule just from the data quite well. But anyway, that was everything I wanted to discuss in this video. I hope you found that useful, and I will see you in the next one.